All right. So in what we are actually going to be looking at for our final set of notes here in physics class, since it is the very last class of the term, I wanted to try and keep it kind of short and simple. So today we're going to be talking about the electromagnetic spectrum, which sounds very big and complicated, but in fact is not really, and is something that you actually deal with every single day without realizing it. And so today we're going to talk a little bit about kind of what are waves and what types of different waves make up the electromagnetic spectrum. Now, we're not talking about like waves that you see in an ocean, although they look kind of like that. Instead, we're talking about the kind of waves that produce radiation, like what we were talking about with our heat movement earlier. So these are waves that carry energy across the universe, across the galaxy, from the sun or from other planets onto our own. So electromagnetic waves in the electromagnetic spectrum. What is it? What are they made out of? And how do they interact with us? So an electromagnetic wave, also a lot of times you'll see electromagnetic shortened to just EM, because that's a lot easier to say and spell. So EM waves are waves that can travel without a medium. So what that means is that things like ocean waves need water to travel through. Sound waves, so the way that you hear things is by waves in the air hitting your eardrums and your brain turning that into sound. Sound waves need air in order to travel through, but electromagnetic waves do not need any sort of medium to travel through. They can travel across the galaxy through empty space. That's how we're able to get things like heat and radiation from our sun, is because they're able to travel through space even though there's no air or water for them to travel through. But these waves still have the same basic properties as a wave that you would think of in the ocean. So they have these up and down patterns where we have these crusts at the top and we have these troughs down here at the bottom. So one important thing that I want to point out specifically about this picture is that the distance from one crest to the other on the wave is called the wave length. So we're going to be talking a lot about wavelengths today. And a wavelength is just how far apart are these crests in the wave. And the ocean, it would be like how far apart is the top of one wave from the top of another wave. And these EM waves, we call them crests, and the wavelength is how far apart that they are. So there are three kind of related things that make up an electromagnetic wave. They are speed, how quickly the wave travels, wavelength, which is what we were just talking about, how long that a wave is, and frequency, which is how often we cycle between going up and down and up and down and up and down. So you can think of frequency kind of like your heartbeat, right? If you're sitting or you're sleeping and you're very calm and still, you have a very low heartbeat where it beats like once a second or once every half second. If you're exercising and moving around a lot, all of a sudden you have a much faster heartbeat, right? So the fewer beats means a lower frequency. The more beats means a higher frequency. So we have this simple little formula to tell us how fast or what the frequency or wavelength of a wave is. Speed of a wave is equal to frequency times wavelength. So if you multiply the frequency and the wavelength together, you'll get the speed of your wave. Now, the interesting thing about EM waves is that they actually all have the exact same speed. So all EM waves travel at the speed of light, which is 3 times 10 to the 8th meters per second. That'd be, hold on, how many would that be? 4 is 1,000. So 8 would be 3 million meters every second is how quickly light travels. Extremely, extremely fast. Literally the fastest thing that scientists have ever studied. And all EM waves travel at that speed. So the speed for all of our waves is the same thing. Incredibly fast. 3 million meters per second, which is the same as 300,000 kilometers per second. Speed of light. So my favorite fact about the speed of light is that light and electromagnetic waves are so fast that they can travel around the world 8 times in 1 second. So if you stop your stopwatch and go 0, 1, in that 1 second, a light or electromagnetic wave could have traveled around the Earth 8 entire times. So very, 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 very fast. What that means for us is that if the speed of the wave is always the same, then that means the wavelength and the frequency are the only things that are changing. And so since we have to keep the speed the same, if one of those goes up, the other one has to go down in order for them to stay balanced. So you may remember from some of our other calculations that we talked about, some of our other formulas, but that means that we have an inverse relationship. If the wavelength gets bigger, the frequency gets lower. If the wavelength, or if the frequency gets higher, the wavelength goes down. So in an inverse relationship, one goes up and one goes down. So if wavelength is up, frequency is down. If frequency goes up, wavelength goes down. So these guys are always going to be going up and down, kind of to balance out with each other. So waves that have a longer, a bigger wavelength will have a lower frequency, right? They're not going to happen as often. Meanwhile, waves that have a really small wavelength, those waves are really close together, so they have a high frequency. They're going to be happening a lot. So all the different types of electromagnetic waves can be put into one kind of handy-dandy chart here that is often called the electromagnetic spectrum, or the EM spectrum. So this is a range of all the different types of electromagnetic waves out there, normally placed in order of increasing frequency. So you can see we have our frequency on the bottom down here. And so our lowest frequency waves are things like radio waves. And our highest frequency rays are things like X-rays and gamma rays, which are like radioactive elements that we get from nuclear material. So if frequency is going up as we go up our spectrum here, that means that wavelength goes down. So the bigger waves So radio waves, for example, are about the size of like a soccer field or a house, right? So the stuff that you're picking up on your car radio, its waves are extremely big. They're invisible, we can't see them, but we've got these really big waves that are traveling at the same speed, but they don't have a very high frequency. We only get about 100,000 waves per second, compared to things like UV rays and X-rays, where now they have a really, really tiny, small wavelength that's down to like the atom level, but we're getting hundreds of billions of them every second. So we can either have really big waves that don't come along as often, or really small waves that have that really high frequency. And all of that makes up the electromagnetic spectrum. So today what we're going to do is kind of talk about each one of these things very, very generally, and go over what types of waves are these and where do they kind of fall on the wavelength and frequency levels. So we'll start with our kind of lower energy waves, our bigger, not slower, but bigger, lower frequency waves up first. So this picture I really like because it kind of shows you that as we increase in frequency, our wavelengths get shorter. So we start off with these really big waves that are not as frequent, but then as the wavelength shrinks, we get more and more and more frequent. So that's why we have this trade-off between wavelength and frequency. It's a simple thing of if your wave is bigger and it's traveling at the same speed, that means that you're not going to get as many of those crests coming by as these smaller waves over here. So things like radio waves and microwaves are relatively long with a low frequency, whereas things like X-rays and gamma rays are really tiny with a very high frequency. So up first, we have radio waves. So these, much like you would suspect, hold on, let me get some dust off my lens here. There we go. Radio waves have the longest wavelengths and lowest frequencies of all the electromagnetic waves. So radio waves can actually be really, really big EM waves, like dozens or hundreds of feet in wavelength. So because of that, they have a very low frequency. Radio waves will only cycle about 1,000 times per second, which in terms of EM waves is not really all that many. So radio waves are used for a whole bunch of stuff. Just like their name suggests, they're what go out over the AM and FM radios whenever you're picking up stuff like on your car stereo. They're also used to map our world through GPS. So GPS, the global positioning system, will actually send down a signal to Earth, to a receiver, which will then send a radio wave signal back to a different satellite. And that will tell the satellites exactly how far away the receiver is. So whenever you're getting like a GPS signal on your phone in order to get directions to somewhere, your phone is communicating with radio waves to the GPS satellites and using that to figure out your exact position on Earth. There we go. So the way that something like your car radio actually works is that you have a receiver that is picking up those radio waves, and then a chip inside of the radio which converts those radio waves to sound waves. So each radio station has a slightly different frequency. So the number on your radio dial, like if you're listening to 93.3 or 96.7 or 101.5, that is actually the specific frequency for that radio wave in this area. So that's the way that you can switch between the different stations, is that they're all broadcasting radio waves all the time, but they're broadcasting them at slightly different frequencies. So if you change the frequency that your car antenna is tuned into, you'll pick up a different radio wave and be listening to different music. So MRI machines, if you ever had to go in to get like something scanned in your head or your body and they give you an MRI, that is also a type of radio waves. These are like a little bit shorter, not as big wavelengths as the one you'd use for a car stereo, car radio. But it uses a combination of radio waves and magnets in order to create an image. I'm not going to go super into detail how it works. A, because we don't have enough time, and B, because I don't really know the specifics myself. But it's kind of like GPS in that it uses how the radio waves bounce off of your body and reflect off the different magnets in order to create an image of your brain or your muscle or your bone or whatever it is that you are getting imaged. One final helpful thing for radio waves is for radar. So radar, like military planes use to see who's flying in their airspace, or police use in order to track the speed of a car, or people at baseball games use in order to see how fast the pitcher threw that pitch. It uses radar to figure out how fast an object is moving by sending out radio waves and measuring how long it takes them to return. So it knows the speed that radio waves are supposed to travel, again, the speed of light. And so it can tell in like teeny milliseconds from one bounce back to the next one, depending on how long it takes. That tells the little computer inside how quickly an object is moving. The further that it travels while the radar is on it, the quicker that that object is moving. All right, so those are radio waves, our biggest wavelength and lowest frequency wave. If we move a little bit further up the electromagnetic spectrum, we have microwaves. So microwave is like at the very, very high end of radio waves. So they have a little bit shorter wavelength and higher frequency compared to other types of radio waves that are out there. And microwaves are used primarily by humans in microwave ovens. Scientists use them for a whole bunch of different purposes as well, including mapping out stuff in the universe, like different galaxies and stuff. But for your everyday, traditional human kind of use, the microwave oven in your kitchen cooks food by emitting microwaves. So you put the food in there, you close the door, you hit a button, and it starts rotating around, and the reason why you hear it go like ooh is because the microwave generator turns on. And the way that microwaves cook your food is that it's not like a traditional oven where it just heats up the air around it and that causes the food to get heated up as well. Instead, these microwaves transfer some of their EM energy into the water molecules in your food. So most food has moisture in it, right? We don't like eating a lot of food that's super like dry and crunchy. We like it when there's a little bit of chew, a little bit of moistness in our food. So microwaves exploit this fact, but they give energy to the water molecules to start vibrating. And like we talked about on Tuesday, when we were talking about temperature and heat, the faster you can get your particles to move, the more temperature that you're going to have. Temperature is just a measurement of how quickly the particles in your matter are moving. If you can get the water molecules to start vibrating, they will start to heat up, and that is what is actually cooking your food in the microwave, is the microwaves exciting the water molecules and those producing heat that cooks the rest of your food. That's why some things don't really heat up very well when you put them in the microwave. Things that are like really dry or really brittle, you can put them in for like 30 seconds and then take them out and they don't really feel that warm, right? If there's not a lot of water in them, then the microwaves aren't going to heat them up as efficiently. These microwaves work really, really well for water molecules. So again, it's not like it's blasting the food with these like heat rays. It instead is sending out these microwaves, and those are passing their energy on to the water, which then takes that energy and turns it into heat and cooks your food. All right, so if you move a little bit further up our electromagnetic spectrum from the microwaves, we get what are called infrared rays. So infrared rays, you can split it up into two words, infra and red. So infra is a fancy kind of science term, science prefix, meaning like below or under. So infrared means below red, meaning that on our electromagnetic spectrum, it's the type of wave that comes right before we start to get into the visible light spectrum, where red is at the very bottom of that. So we're going up the spectrum, which means that our wavelengths are getting shorter and our frequencies are increasing. So infrared waves have shorter wavelength and higher frequency than microwaves. So infrared rays are really neat because they are produced by heat. They're a type of radiation, a type of electromagnetic wave that is often given off from your body when it also gives off heat. So warm objects give off more heat energy than cool objects, obviously. And so we can measure how much infrared rays are coming off of an object and produce an image like this. So a thermogram are these fancy images. You've probably seen them on like cop shows and stuff where they're trying to figure out where people are moving, like inside a building. So they calculate how hot a certain area is by measuring the amount of infrared rays that are given off, the amount of infrared radiation coming off of that object. So the warmer something is, the more infrared rays that it is producing. That's why, like, if you take an infrared ray of somebody's body, you'll generally see that their like chest and head tend to be really warm, whereas their fingers and toes are a little bit cooler. And that means that there's more infrared radiation coming off of like your palm. So your palm tends to be pretty warm because like your hand is naturally a little bit closed, keeps that warmth in. Same thing if you're looking at a building, you can generally see that areas of like doors and windows and cracks in the building and stuff that are giving off more heat will give off infrared waves as well. So normally with our human eye, we cannot see these infrared rays. But by looking at something that can detect infrared, we can see, okay, this area is warmer because there's more infrared radiation coming off of it than this cooler area over here. So it takes that information about how much infrared rays are coming and turns it into this nice kind of thermogram, this nice picture of hotter areas and cooler areas. All right. If we move on to the most exciting part of the spectrum for us humans, at least, that is the visible light spectrum. So we're moving on from infrared rays. So now we're getting into shorter wavelengths, so really, really small wavelengths, hundreds of a meter, I should say. And higher frequencies. These waves are getting closer and closer together, so they're happening more often. So these are the electromagnetic waves we can see, which is why we call it visible light. So not just the light, but the colors as well that are a result of the light are all types of electromagnetic waves. So red light has the longest wavelength. It's down at kind of one end of the spectrum. And violet or purple light has the shortest wavelength. It's up at the other end of the spectrum. So the rays that we were just talking about, the infrared waves, they're called infrared because they have longer wavelengths than red light. So red is kind of the bottom wavelength for human vision, and infrared has a frequency and wavelength below that. So violet is kind of the top end of our wavelengths and frequencies in terms of visible light, the shortest wavelength and the highest frequency. And so the next wave that we'll be talking about after this is given a name meaning above violet, also known as ultraviolet. We'll focus on visible light for now. So again, we talked about radio waves, we talked about microwaves and infrared waves. And now visible light makes up this kind of part of the spectrum right here before we start getting into things like ultraviolet rays and X-rays. Again, the red light has the longest wavelength and the violet light has the shortest wavelength. So the red light wavelength comes right after our infrared, and the violet wavelength comes right before our ultraviolet. So you probably are, oh wait, no, it's supposed to do like a thing. Dang it. These are supposed to, oh wait, maybe it'll. I guess not. It was supposed to show the wavelengths breaking up into the different colors. So when light enters a new medium, it bends, also known as refracting. And so as it bends, it goes through its different wavelengths, and that's what gives us the different colors. So visible light being refracted in a certain way produces a certain color. And you probably know those mostly, like we were just seeing earlier, as the colors of the rainbow. Oftentimes abbreviated as Roy G. Biv. For red, orange, yellow, green, blue, indigo, violet. So as the light gets refracted more and more, it gets a shorter and shorter wavelength, And so to our eyes, the light changes color. So this is what produces rainbows, is light refracting through things like water droplets in the atmosphere and producing these big rainbows in the sky that show all of the different colors that light can be split into. And yeah, I'm really bummed that these GIFs didn't work. They looked really cool. All right. Anyways. So that is our visible light portion of the spectrum. This is the electromagnetic spectrum that we as humans can see with our own eye. We can see colors, we can see the different combinations of these colors, and all it is light waves that are being reflected or refracted and bent in different ways in order to change their wavelength. So if we keep moving up our spectrum, we're starting to get into the really intense types of electromagnetic waves. And the first one we're going to talk about is ultraviolet rays. So again, purple and violet are at kind of the top end of our visible spectrum in terms of their short wavelength and high frequency. Ultraviolet is even above that. So we can't see ultraviolet waves anymore. They're not detectable by our human vision. There are some animals that can see ultraviolet. There are certain types of reptiles and birds who do have the ability in their eyes to pick up on ultraviolet rays. It produces, to their eyes, at least as far as we think, a kind of different type of coloration. But these guys have more energy than visible light. And so we've got these short wavelengths with these pretty high frequencies now. So UV rays are really useful in different ways. A lot of times things like laboratory equipment is sterilized by UV rays because they will kill bacteria. Bacteria cannot handle the amount of energy that's blasted at them if they're underneath like a direct UV ray light. And so it'll kill off those bacteria by basically kind of overwhelming them with energy and burning them out without having to actually set your lab equipment on fire or wash it in some sort of alcohol-based solution, which could mess it up. So UV rays are really helpful for stuff like that. They're not so helpful because they're intense enough not just to kill bacteria, but also to affect our skin as well. So UV rays are what cause sunburn on your body. So if you're going outside for multiple hours, especially in the spring and summer here in Texas, and you forget to put sunblock on, you're going to have a bad time, right? Your skin is going to get burned by the intensity of these UV rays. Obviously, it doesn't just happen if you're outside for 10 or 20 minutes walking around. But if you're out there for a couple hours, that elongated exposure exposes your skin to enough UV rays in order to that it gets burned. Even more of a downside of UV rays is that if you get enough UV rays over your lifetime, that puts you at an increased risk for developing skin cancer. So UV rays mess with the DNA inside of your cells if they are sitting in the UV for too long. And if that happens too much, you could end up with cells that become cancerous and start forming tumors, which is not good. That's why sunscreen is so incredibly helpful. Not only does it help prevent you from getting sunburn, it also can help prevent skin cancer. And it's all because the material that they put in sunscreen blocks the UV rays. It basically causes the ray to come in and be reflected from your skin instead of being absorbed and causing burning or increasing your risk for skin cancer. So if you're going to be outside for more than like 30, 40 minutes, especially in the late spring and summertime in Austin, definitely highly recommend putting on some sunscreen, some sort of sunblock. The SPF on the sunblock, the sun protection factor, essentially tells you kind of how strong or how good it is at blocking those sun's rays. One science hack that I will tell you right here is that anything above like an SPF of 50 or so is only give you very minimal extra protection. So they might give you like a really big number, like SPF 70 or 80. But the reality is that even lower SPFs, like things that are SPF 30 or 40, will block out like 80 to 85% of the UV rays from the sun. I want to say once you start to get up into the really high numbers, like SPF 50 will block about 90% of it. But then if you go up to like SPF 70, it'll block like 93% of it. Or SPF 100 will block like 96%. So you're really not getting all that much more protection, even though it looks like, whoa, that's twice as big of a number. It might be twice as good. Not really. As long as you put on something that has SPF, especially around like 35, 40, that'll give you plenty of protection from the harmful UV rays from the sun. All right, so ultraviolet rays are kind of the first types of rays that can cause damage if they get too much exposure. One other benefit of UV rays, though, is they would actually stimulate your skin to produce vitamin D. So vitamin D is a really helpful vitamin for your body. You can naturally produce it, but it really only is produced when you're in the presence of ultraviolet light from the sun. So that kind of is what stimulates your scales. It allows them to break down these certain cholesterols and turn it into vitamin D, which is good for your teeth. It's good for your bones. It's good for your immune system. It's good all around. So a little bit of sunshine in the course of your day is a very good thing. A lot of sunshine can start to go bad. All right. What about some of the really powerful rays that we have discovered and harnessed for our own use? So moving up the chain from ultraviolet rays, now we have X-rays. So now our wavelength is getting even shorter and tinier, like the size of an atom type wavelength. And the frequency is getting much higher. So ultraviolet rays carried a lot of energy. X-rays carry even more energy. So there's a ton of energy stored in X-rays. The handy thing about them is that they can penetrate through most matter. That's what makes them useful for taking pictures of things like bones and teeth. So bones and teeth absorb the X-ray. So whenever somebody takes an X-ray, like at the dentist office or at the doctor's office, they set up the camera, then they usually set up some sort of backing. And the way it works is they shoot X-rays down at that area where the camera is pointing. Most of those X-rays will bounce back and be reabsorbed by the camera, but some of them are absorbed by X-ray absorbing material like bones. So the material that gets bounced back is things like skin and muscle, so that doesn't really produce a strong image. But the stuff that gets absorbed and not bounced back produces this really clear image. So it allows us to see underneath the skin. So they're super duper helpful in this way. They're used to look at broken bones or like what's going on inside of someone's kind of gastrointestinal system, because you can see like minor changes in the X-ray absorption that could tell you something bad is going on. But too many X-rays is definitely a bad thing. There's a reason why whenever they're about to take one, everybody kind of clears out of the room or wears some sort of protective covering. And that's because too much exposure to X-rays causes cancer. So just like I mentioned with the ultraviolet rays, they have a lot of energy that can harm your cells and cause them to start being cancerous. X-rays have exponentially more energy than ultraviolet rays. So an extended exposure to X-rays over a long time dramatically increases your possibility of developing some sort of cancer. So that's why X-ray technicians are always very careful when they're taking them. If they have to be in the same room, they'll wear these padded lead-lined vests because lead blocks X-rays. It prevents X-rays from passing through. It's one of the few things that is resistant to X-rays. So by wearing these lead coatings, they're able to stop their cells from being inundated by the X-rays. 1 or 2 or 3 X-rays over the course of your lifetime, or even over the course of like a year or so, probably isn't going to cause that much damage to your cells. But for people like dentists and technicians who are taking X-rays of different people every day, they definitely need some sort of protection to stay safe. So besides looking at bones in humans and animals, X-rays can also look at bones, quote unquote, in structures. So engineers will use X-ray technology in order to look at concrete structures, to look for small cracks or things that are not supposed to be there. So just like with the bones, most of the concrete in this case will absorb the X-ray and it'll show up as this white color. But if there's a crack, the X-ray will pass through and not get absorbed, and it shows up as this darker black color. All right, and then finally, up at the way top end of the electromagnetic spectrum, some extremely, incredibly powerful and dangerous rays are known as gamma rays. So these have the shortest wavelength and the highest frequency of the electromagnetic spectrum. These wavelengths are incredibly tiny, 10 to the negative 12th meters. So we're talking down at the level of like protons and neutrons here. That's how far apart these waves are. And we can get billions and billions of them in a single second. So 10 to the 20th would be a 10 or like a 1 followed by 20 zeros. So we're talking like the billions of billions for their frequency. So extremely high energy waves. So gamma rays are essentially what are produced by radiation. So when you think of like producing nuclear fission or using types of radiation to kill cancer cells, gamma rays are the types of radiation used. So they are extremely dangerous. They can be very harmful if they're not used correctly and at a very specific kind of dosage and very specific level. But these, if they're not used carefully, could give people cancer very, very easily or produce all sorts of other burns and diseases. So gamma rays are possibly most famous because back when Stan Lee was creating Marvel characters like the Hulk, he used gamma rays as the thing that gave the Hulk his superpower. So it was a scientist, Bruce Banner, who was working in some sort of nuclear lab and then accidentally went into one of the chambers and was blasted with super powerful gamma rays. And for normal people, you'd either die or develop like super cancer. But instead, Bruce Banner developed this super crazy strength of the Incredible Hulk. So whenever you hear about like nuclear fallout or like a nuclear accident happen or a nuclear explosion goes off, the radiation that's emitted is in the form of gamma radiation. So these are super powerful, super toxic, super dangerous rays. the amount of energy that they have, that super tiny wavelength and super high frequency, makes them extremely dangerous towards living cells. All right, so just a little brief review of what we talked about so far. We mentioned that speed and frequency and wavelength are all related with our electromagnetic waves. So the neat thing is that they all travel at the same speed, 300 million meters per second. So that means that only their wavelengths and frequencies will change. If you have a really long, big wavelength, you're going to have a low frequency. If you have a really tiny, short wavelength, you're going to have a higher frequency. And the higher the frequency, the higher the energy. So things like radio waves and infrared waves have relatively low energy, but things like X-rays and gamma rays have extremely high energies. So as we go up our electromagnetics chart, we're getting into smaller and smaller wavelengths, but that means we're getting bigger and bigger frequencies. All right, so that's just kind of a very simple, basic overview of what electromagnetic waves are, how they're related by frequency and wavelength, and what are the different common types that make up the electromagnetic spectrum. So does anybody have, I know it's just a whole lot of me talking at you guys there, but does anybody have any questions on the different types of EM waves or frequency and wavelength and how they're related, or anything from the notes that I was just going over? Any questions about anything? All right, it doesn't sound like it. So since this is the very last day of the term, I wanted to have it be a fairly simple and kind of straightforward worksheet for you guys to do. So the question should be pretty straightforward. The first one is just a simple question about the three main properties of EM waves, and then a little bit about how frequency and wavelength are related to each other. And then the second part down here, I have listed out the different electromagnetic waves that we've talked about. And I want you to match these waves with the type of description that's given. So which waves do we see that produce color? Which waves have the shortest wavelength and are highly radioactive? Which waves do we use to calculate temperature? And which ones take pictures of bones? So each one of these descriptions should match up with one type of electromagnetic wave across the top here. Like I said, pretty short, simple, and easy, but I wanted to make it that way so that you had plenty of time to work on other stuff for your classes or stuff for this class if you needed to as well. Again, this is the last day of the term, so please make sure that you get any worksheets that you are still working on turned in. I know Frishta, there are a couple that you had been working on that were still kind of halfway done. So do your best to get those finished up and turned in by the end of the day today, so that you can make sure you get credit for getting those completed. Alrighty, guys. Does anybody have any final question on the EM waves or the homework or anything else related to the end of term 4 here?
Excuse me, I have a question.